Okay. So guys, let me sort of lay out the path of the day. So what we're going to do to wrap up our time with voltaic cells and batteries is to talk about what happens when a battery dies. You guys all understand that batteries create voltages, and just like water running downhill, eventually you run out of water. Well, guys, batteries are a little bit different, and maybe it would be helpful to watch my hands because this is one of the places where the analogy falls apart. We think about voltage as water pressure, right? And in the same way that we understand that our water system, well, maybe you now understand that our water system has a pressure because we store our water at a higher elevation. Okay, and so we think of those elevations as differences in potential which create pressure, which we call voltage. Well, guys, here's a place where the analogy falls apart. If the water were to stop flowing in Orem, it would be because the tank is empty, right? Kind of makes sense. But with a battery, the water, the electrons don't stop flowing because we've run out of electrons. They stop flowing because they come to the same elevation. Kind of. It's almost as if magically, as the water flows out of the tank were to drop. This is, okay, so what about this? Sort of, but what about this? What if somebody were allowed to build a house high enough on the hill above 800 North in the old Word Perfect campus in the cemetery? What if somebody were able to build a house up there where the upper floor was higher than the bottom of the water tank? See what I'm saying? So if the water tank were full, there would still be a higher elevation in the water tank than their bathroom fixtures on the top floor, and water would continue to flow. But eventually, as this dropped, when it reached the same elevation as their third floor bathrooms, water would no longer flow into their house. You get the idea? So guys, this is not a bad analogy. This just hit me. So guys, when we reach that point, which direction could the water flow? In either direction, and it would be at equilibrium. Guys, the same thing happens in batteries. What happens is the pressure or the reduction potential at the cathode and the anode actually become equal, and at that point the voltage, well, the electrons cease to flow. You get the idea? So how does that happen? I wonder if this is going to work. Just a second. Oh, nuts. Hold on. I lost. Did I restart my drawing stuff? Wait, hold on. Sometimes it comes back if I do that. No. So guys, let's talk really quickly then about how this happens. So remember the thing that we looked at, and I'm going to do an even worse job of doing this than before. And this was silver, and this was silver ion, and this was iron. I'm not even going to hook them up. And this was iron ion, and it was going this way, right? So that makes this oxidation, so it was going this way. Is that right? And then this was reduction, so it's going this way. Am I good? Okay. Now, guys, let's talk about this. And actually, let's bring into this what Ben mentioned. This was really great. So if we were to write the net ionic equation for this, actually, let's go ahead and balance it. You okay with it being that? Did I do that right? No. Thank you. Yeah, that should be going. Is that okay? Did I do that right? Okay. So guys, here's the question. As this battery does its battery thing, what kind of changes are we experiencing in these cells? What's happening over here as this battery functions as a battery? What's happening to the amount of iron in the strip? It's going down. Where's it going? into solution. So what is happening to the molarity of this solution? Careful. What's happening here? The molarity is going up. The concentration is increasing. What's going on over here? The molarity is going down. And guys, here's what ends up happening. Eventually, this molarity goes up so much and this molarity goes down so much that it creates a concentration imbalance that overcomes the voltage imbalance based upon their reduction potentials. And when the voltage gradient is offset by the concentration gradient, the battery dies. Does that make sense? So the idea is this, guys. Let me switch colors and let's try this again. So here's the idea. Which one of these is a better electron spitter-outer? The iron or the silver? Iron, right? So we think of that like the iron being at a high elevation and the silver being at a low elevation, and this difference in elevation creates a voltage pressure, right? Well, guess what? What is happening to the concentration of this? It's going down. What's happening to the concentration of the silver? It's going up. And guys, when this difference in solution concentration offsets this difference in reduction potential, the battery dies. It's kind of like all of a sudden you're trying to push water uphill, because as we said, as the concentration of this goes up, it fights against the voltage, right? Remember we said if we made this 10 times more concentrated, the voltage goes down? Well, guys, what's happening to the battery as it does its thing? The concentration is going up, right? We don't have to artificially make it 10 times more concentrated. It's making itself more concentrated as it's a battery. And similarly here, what did we say would happen to the battery as this concentration goes down? The voltage would go down. Are you guys not catching this? Is that okay? The voltage goes down, but that's what the battery is doing to itself as it does its thing, and eventually this becomes so concentrated and this becomes so dilute that that concentration gradient offsets the voltage gradient and the battery is dead. Is that okay? So guys, what then is really happening to that battery at these conditions? Is nothing happening? No, it's actually flowing in both directions simultaneously, which we call equilibrium. Do you get the idea? Is that okay? Yeah. Electrons are going to silver. Yes, both directions. Yeah. So how can they go backwards? And the reason is because there's so many iron ions over here in solution that there's such a positive charge over here that it sucks some of the electrons backwards. Yeah, which is another way to think about why it dies. Robbie. That's interesting. Yes. And yes. So it's really just a different way of thinking about the same thing. We could have this entire conversation that we just had based on the salt bridge. Instead of thinking about the gradient, because when you say polarized, what polarized means is creates a gradient, right? You could have this entire conversation about why a battery dies, not based upon the balance between the electrical pressure, the voltage, and the concentrations. You could have the same concentration, you could have the same conversation based upon the polarization of the salt bridge and the concentration gradient in the cells. But I would hate to go there because some people could get so spun around in that, because the whole conversation would be the opposite. That yes, but let's not talk about it, because it's more important to understand it as the interplay of the voltage and the concentrations. Is that okay? Go ahead. Are we okay? So guys, let me explain to you what we're going to do then given this. To wrap up today, the first thing that we're going to talk about is how does this battery behave as it goes to equilibrium? Because what happens at equilibrium? It dies, right? So what happens to the battery as it goes to equilibrium? And you know part of the answer. What happens to the concentration in the anode? goes up. What happens to the concentration at the cathode? It goes down. We are going to track those changes because, guys, remember, this is our this is our anode, right? And this concentration is our cathode. But what did I just write down? The Kc expression. So we can actually track this battery as it dies by talking about Kc. Then, guys, to finish out the day, what we're going to do is, once we understand how batteries die, we're then going to quantify when the battery is actually dead, and we'll be able to predict at what conditions is it finally fully dead. Get the idea? Okay, so here we go. Dun, dun, dun. Psh, psh. So it goes like this. Guys, the beginning of this is conversational. Be judicious in what you write down. So here's where we're at right now, guys. Up until now in our study of voltaic cells, and remember we left voltaic cells for a minute or two last time, right? And we genericized the voltaic cell equation, and instead of saying cathode minus anode, we said reduction minus oxidation. We're back to voltaic cells. So guys, these are the things that we've agreed on. All voltaic cells are spontaneous. Why is that true? Because if they weren't, they wouldn't be a very good battery. But we also understand that when we say they're spontaneous, all of these cells are spontaneous. They just might be spontaneous in the other direction. But guys, if they are all spontaneous, what are their voltages? Positive. So positive voltages tell us that they're written properly in the spontaneous direction. Now guys, this is something that we didn't directly touch on, but if you look at your oxidation reduction potential chart, you'll notice that it mentions aqueous solutions at 25 degrees Celsius. So we find out that the conditions at which this is actually true is temperature dependent, but it is also molarity dependent. So guys, all of the numbers that we have been talking about up until now have been understood to be at 25 degrees Celsius at 1 atmosphere of pressure and 1 molar solutions. Now guys, why is that important to us? Go ahead. It depends on the particular reaction there, because some of the reactions that you were doing in lab should have been 1 molar solutions. And in those 1 molar solution reactions, they should have been right on. In others of them, they could have been fractions, but not a tenth. Cutting the concentration by a tenth does not directly cut the voltage by a tenth. And you'll see why in a minute. Yeah. Yes, and guys, that's the thing that I wanted to bring us to. Oh, poop. I didn't hit W. Oh no, now I'm going to be ghosting, aren't I? Maybe I'm okay. W. Where'd it go? Okay, I know I didn't erase my drawing. So where did it? Oh, I did it again. Okay, out, back. Come on. Oh, now I'm really in trouble. Okay, it's gone. Really? Okay, let's just quit out of this. Now are you there? I hate this program. All right, so guys, we understand now that concentration is an issue, right? And did you hear what Ben said? And I know that not all of you are in lab, but for those of you that are, you're fine. For those of you that aren't in lab today we started building batteries. And Ben said, is concentration why it was important that when we measured the voltages, we did it right away? And the answer is yes, and here's why. Guys, when you hook this battery up, say that we're starting with 1 molar solutions. So this is 1 molar iron and this is 1 molar silver. The minute you hook that battery up, the second, these are both 1 molar solutions. But then immediately what happens to the concentration of this? Becomes more than 1 molar, and this becomes less than 1 molar, and that means the voltages will start to change. What will they do? They will drop. right? And so, guys, all of these pretty numbers that we've been digging off of our oxidation reduction table only work at the moment we create that battery, assuming that they are all 1 molar solutions, and any time after that, the molarities will no longer be 1 and the voltages will change. Go ahead. Oh, that was just water bottle lifting? No, you're good. Okay. So now, guys, what we need is this. We need to now be able to track the actual things that these batteries do. And you know what, guys, I would say don't write any of this down. It's all preliminary. So, guys, we understand this now, right? And I wrote it as a question. What happens to the concentrations of the reactants, the ions, as the reaction takes place? And let's see if we can answer this without a diagram. What happens at the anode? Does the concentration go up or down? Up, down. Anode is oxidation, so the metal is going into solution as an ion. So at the anode, the concentration goes up, and at the cathode, then conversely, it goes down. So, guys, which one is increased? The anode. The one that is decreased is the cathode, and we've already talked about that. But then, guys, eventually what happens is this thing reaches equilibrium. And when a battery reaches equilibrium, what does the voltage become? 0. And that battery is dead. Yes? Okay. So, guys, with that said, then, what we're going to do is we are going to quantify this using this equation. Yeah. Yeah, actually, you know, good for you. Yeah, it's actually called a concentration cell. If you look, and Garrett, it's neat that you see that. So we used, the next slide after this, when I first started teaching AP, was concentration cells, and they took it out of the curriculum. So I deleted the slide. Yeah, look on page 852. So, guys, we're not going to spend a lot of time here, but Garrett brought up an interesting point. Doesn't that then mean you should be able to build a battery out of 2 of the same metals? Copper and copper, zinc and zinc. And the answer is absolutely. Realize that if you've got 2 of the same metals, what does the math work out to when you do cathode minus anode? 0, right? So the voltage is not being created by dissimilar metals. You can actually create a voltage by using different concentrations. But now I get to turn this back to you as a question. Which one would be the anode and which would be the cathode? So the cell with the higher concentration, which one would that be? Be the cathode, because that's where you'd get reduction, right? You've got more ion to be deposited, reduced as the metal. So the higher concentrated cell would be the cathode, the lower concentrated cell would be the anode. But what you'd find if you do the math is they're functionally worthless. You're creating hundredths of a volt through those concentration differences. So they took it out of the curriculum. Yeah. So it's not a great way to build a battery. No, because again, eventually what would happen is you would end up with those concentrations resetting to equilibrium, right? Because the one that is the higher concentration, again, would be the cathode, right? But what happens at the cathode? Those ions are being deposited as solid, and that concentration's going down. Conversely, the other concentration's going up. Eventually, they become equal, and the battery still dies. Well, you can reset any battery. But a concentration battery wouldn't be any more long-lasting than any other battery. They're all going to die. Yeah, all batteries die. Okay, so guys, let's talk about this equation, because this is the equation that allows us to figure out the voltage of a battery anywhere from the moment it starts out to death. Okay, so have you written it down? Let's talk about what these things are. So guys, first of all, E sub cell. This is the voltage of the battery anywhere along its life path. Okay, now, what is E naught cell? What does the naught tell us? Standard conditions. So this is the value that we can calculate by doing cathode minus anode. This is the voltage of the battery at standard conditions, which again we lift right off of our reduction potential chart. Now guys, what is N? Moles of what? Electrons. N is the number of moles of electrons. Now gang, do you remember Q? You've already met Q. When we learned about Kc, we said that we can also calculate this value called Q, which allows us to predict the direction that reactions will proceed towards equilibrium. So what is Q? K at non-equilibrium conditions. So this is still products divided by reactants, molarities. It's just at non-standard conditions. So Q is what we call the reaction quotient. Recall that it's the same as Kc, only not at equilibrium. And again, guys, in the past, we used Q to predict which direction a reaction goes as it proceeds to equilibrium. Now what we're going to do is we are going to use Q to figure out how a battery is affected by being at conditions that are not standard, but it's still products divided by reactants. Okay, so guys, we don't need to talk about where 0.0592 comes from, but let's do this. You ready? Just sort of think through this with me. What does the value for N always have to be? Positive whole number, right? It's number of moles of electrons from the balanced equation. This has got to be a positive whole number. What do these values have to be? Positives, right? But, you ready for this? What if this number is bigger than this number? Then what's the value of the fraction? Bigger than 1. What's the log of a number bigger than 1? Positive, right? Guys, track along. So if this value is greater than 1, that means there's more products than reactants, yes? Think about this, guys. If there's more product than reactant, then this fraction will be larger than 1. What is the log of a number larger than 1? Positive, right? What are the negative logs? The ones that are smaller than 1. So guys, do this with me. Maybe we should write this down just to make sure you're clear. Reactants yield products, right? Equilibrium. Okay, so here's the idea. If products are high and reactants are low, then this is bigger than this. What do we get when we divide these through? A number bigger than 1. The log of a number bigger than 1 is positive. So that makes this positive. Now, this will always be positive, and a positive times a positive will always be positive, but we will subtract it. So what will those conditions do to the voltage of the cell? Make it smaller. Does that make sense? Because if this is a fraction bigger than 1, then the log of that number is positive. This is always positive. Positive times positive is positive. And we're now subtracting that positive value, which makes the value negative. Now, why would that be true? Well, that's because there's more product and less reactant. That means it's harder for the battery to go this way, and the voltage goes down. Get it? Okay, now what about the other scenario? Now, what about this? What if we now have, going back here, more reactant and less product? If we're on that side of equilibrium, well, now product is low and reactant is high. What does that do to the value of the fraction? Smaller than 1, not negative, but smaller than 1. What is the log of a number smaller than 1? Negative. A negative times a positive is a negative, but now we're subtracting a negative, which really means we are adding and the voltage goes up. But doesn't that make sense? If we've got lots of reactant and not much product, we would expect the voltage to go up because that'll drive the reaction forward, increasing the voltage. Good? Okay, go. I have no idea. I don't know, but it's not germane to this conversation. Okay, so guys, do you understand the concept behind the math? Okay, now let's talk about this in a different context. I don't think you need to write this down, but let's talk about it. You ready? This is coming now full circle. What color is this? Blue. Right? Copper solution. Got our piece of zinc soaking in here. Guys, this was the very first voltaic cell that we talked about. We saw it in still pictures, we saw it in animation, we saw it in video, and then we drew it on our paper. Okay. So guys, what is the Kc for this expression? What does it look like? Let's do this together. What does Kc look like? Concentration of? What? So it's products divided by reactants, right? Yes? Yeah. So it's the So guys, it's the concentration of zinc ion, thank you, divided by the concentration of copper ion. Yeah? Okay, now what about, again, the solid zinc and copper? They're solids and they don't go in there. Okay, so what about this? How many moles of electrons are being exchanged? Yes, but how many moles of electrons are being exchanged? 2. How many is zinc losing? 2. How many is copper gaining? 2. So what's the value for N? 2. So this is 2 electrons. Question number 3. It's not really a question. The voltage of this battery is 1.10 volts at standard conditions. How do we know? Cathode minus anode. Look up their reduction potentials. We saw it in that fake little voltmeter. Remember 1.1 volts? Okay. So now, guys, this. What would the Nernst equation look like for this reaction? If we fleshed out Nernst, what would it look like? Well, we start with E cell. Then, and I'm not going to write out, remember when you use an equation, you write it out first, but what's the next thing we run into? E naught cell, which is what? 1.10 volts. You know what? I better write this down up above. I don't think I can undo this much, but let me try. Oh, 2 away. That was pretty good. So guys, I'm going to actually write this down up here so that we have it handy. So we have E cell is equal to 1.10 volts minus, is it 0.0592? Divided by 2 times the log of zinc and copper ions. Good? Okay. So then, guys, maybe what I can do once I've done that is I can just erase these because we've already applied them in context. So now some questions for you. What could we do to this battery to make the voltage go up? Okay, now where are you getting that from? How do you know that adding copper ion would make it go up? Are you looking at red or blue? I'd look at blue. How do we know from blue that adding copper ion would make the voltage go up? Le Chatelier's principle, right? That's where Ben got us thinking a little while ago. Adding reactant will shift the reaction to the right. So one of the things that we could do is we could add copper ion, and that would shift the equilibrium to the right, increasing the voltage. What else could we do? Precipitate out the zinc, right? If we could pull the zinc out of solution, decreasing this would also create an increase in voltage, Le Chatelier's principle. Now, guys, let's try to tie that back to the math. Remember what we said, increasing copper. Let me see if I can do this here. We'll go blue. So, guys, increasing copper would make the voltage go up. Why, again, is that true? Increasing that makes the value of the fraction go down, making the log of that value more likely negative. As that becomes more likely negative, then the whole value we would end up adding, because a negative times a positive is negative, and you get the idea, right? Is that okay? Okay, so guys, what if we go in the other direction then? What about this? What could we do to make the voltage go down? The other stuff, right? What could we do to copper? Make it go down, or what could we do to zinc? Make it go up. Now guys, this is where this kind of gets sobering, and it comes back to Garrett's question. So guys, what if we do this? What if we get all sorts of crazy, and if we make the copper ion solution, sorry, I forgot to subscript the charges. What if we make copper ion solution 5 molar, and if we make the zinc ion solution 0.05 molar? What will that do to the voltage? Will it go up or down? So let's look. Copper goes up, right, because that's more concentrated than 1. Zinc goes down, less concentrated. So we did both. We increase copper and we decrease zinc. Both of those, zinc ion solutions, both of those changes would make the voltage go up, right? Here's the question. How much? You ready to be wildly disappointed? Let's do the math. So our zinc ion concentration is 0.05. and our copper ion solution is 5.0. So what does this then look like? I'm going to switch to red so it stands out. So this would be 1.10 minus 0.0592 divided by 2 times the log of 0.05 divided by 5 is 0.01. So now guys, doing that math, the log of that, multiply that by 0.0592, divide that by 2, add that now because it's a negative to 1.1. Oh, I did that wrong. So 1.16 volts. So guys, we created a concentration gradient on the order of 100 times. This is 100 times more concentrated than that. That's a pretty steep concentration gradient, and it bought us 0.06 of a volt. So now, Garrett, think about this. What if these were both copper and both zinc? Or both, let's do both copper. Say that these are both copper. We said copper plus copper, and so how would that change if, you talk concentration cell. What if we did that? What if we used two of the same metals and only generated a voltage based upon the concentration gradient? How would that change the Nernst equation? What's this going to become? 0, right? So now the only place that you're generating voltage would be from the concentration gradient. And if you did copper with copper and made one copper cell 0.05 molar and made the other copper cell 5 molar, you get 0.06 volts out of it. Not much. So yeah, not much. But still, your thought was valid though. So guys, you good on Nernst? You get the idea? We got one more thing to, oh, yep. It's on the equation sheet, isn't it? Tell me this is on the equation sheet. Is it not? So I'll give it to you on the test. You don't have to memorize any equations or constants, but I never know how can this not be on this sheet? No. Okay. So guys, let's wrap this up. You ready? This is kind of a neat way to ride this into the sunset. Equilibrium. And guys, again, we are going to do this through a series of of questions. You ready? Last slide of AP Chemistry. Okay. So guys, remember what we did last time. We stepped out of the world of batteries and we started to talk about generic redox reactions. We can kind of do the same thing with Nernst. Whether it's a battery or not, we can use the Nernst equation to look at equilibrium. Now to do this, we need to make some interesting observations. So guys, go back to the idea of reaction quotients, Q. What is the relationship between Q and K at equilibrium? They are the same, because what is Q? Q is K, not at equilibrium. But if the reaction is at equilibrium, Q is K. Is that okay? Okay, now what about this? What is the voltage of a battery at equilibrium? 0. It's dead. There is no potential. So now, guys, watch what we can do. Here's the Nernst equation, right? But look what we did. This is now the Nernst equation for a dead battery. What is the voltage of a dead battery? 0. What is Q for a dead battery? K, because it's at equilibrium. But now, guys, look at what we've got. We now have a relationship between voltage and K. Remember, K is products divided by reactants at equilibrium. And guys, if we solve this for K, thank you. You want to say it again? I have to confess I did too, because the minute I knew what was coming and I was thinking, this isn't on the equation sheet either. All right, here you go. Q is K, battery's dead, Nernst equation, solve for K. But guys, the idea is this. If you know the number of electrons that a battery is swapping in moles, and if you know the standard voltage of the cell, you divide the product of those by 0.0592 and it gives you the log of K. It gives you insight into the equilibrium constant for that reaction. Now again, this is not on the, it's not there, is it? Okay, but we will do some homework assignments relative to it. So guys, here's your homework. That's it. All right, we went out with at least a thud, if not a bang. So guys, now what I'd like to do with about the last 5 minutes of class is I'd like to just have you guys study while I play some copyrighted songs in the background and see if I can get my other YouTube channel shut down for copyright violations.